Hello students. Today we are going to see about design of singly reinforced beam by working stress method. Okay, so the problem is given. So read carefully. So first step is write the permissible stresses of materials. Here the grade of materials like M20 grade and Fe415 steel. Therefore, the corresponding permissible stresses like sigma CBC equal to 7 Newton per mm square and sigma ST equal to 230 Newton per mm square. The second step is to find the dimension of beam. So we don't know about dimension. Okay, this is the trial and error method. So we find the depth of the beam from deflection uh, formula for simply supported condition as per IS 456. The basic L by D basic value equal to 20. So L is span of the beam, D equal to effective depth. So from that we find the effective depth of the beam like 0.2 meter. So according to IS 456, the uh, effective we can provide effective cover as 50 mm. Therefore, overall depth equal to small d plus effective cover, which is nothing but 250 mm or 0.25 meter. Okay. Then next step is load calculation. So, what are all the loads to be acted on the corresponding beam? Okay. So normally we can take the self height of the beam and service load and uh, so both of the load we can take for singly reinforced beam. So first one, self height of the beam, okay, in terms of kilonewton per meter, which is nothing but the unit weight of the RCC, like 25 into uh, the width of the beam is uh, we assumed as zero point 0.3 meter or 300 mm. Therefore, multiplied by zero point 0.3 into the depth of the beam, that is 250 mm or 0.25 meter. Okay, so if you want to find the self height of uh, any member, which is equal to B into capital D into unit weight of RCC, which is nothing but 0.25 into 0.3 into 25 equal to 1.875 kilonewton per meter. Then service load or live load equal to 5 kilonewton per meter, which is given in the problem. Okay, so therefore total load equal to say W equal to 6.875 kilonewton per meter. Okay, and third step is find the effective span of the beam. Okay, effective span of the beam. So clear span plus effective depth are uh, uh, center to center to the distance of support. So we can take least of both values according to IS 456. Therefore, L equal to 4 plus 0.23 by 2. Here support thickness as zero point 0.3 for your problem. Therefore, we can take 4 plus zero point 0.3 by 2 plus zero point 0.3 by 2 because center to center distance. Okay, therefore L equal to 4.3 meter. Then clear span plus effective depth. So 4 plus zero point 0.2 equal to 4.2 meter. So whichever is less, therefore effective span equal to 4.2 meter. Okay, this is trial and error method, so we don't know. So for this support condition, for this load condition, how uh, will we provide the dimension, we don't know already. Okay, so it is trial and error method. Okay, so next step is to find the bending moment and shear force calculation. So for simply supported condition, the bending moment formula is WL squared by 8. Okay, W is total load, L equal to effective span. Okay, therefore moment value is 15.159 kilonewton meter. Then shear force equal to WL by 2. The value is 14 point something. The next step is check for depth, because the depth is assumed. Therefore, we have to check the effective depth according to IS 456. D equal to root of m by qb. So q is design constant. So m is bending moment. B is width of beam. So apply those values in this formula. Then we will get small d as 236.948 mm. Okay, so this is required depth, but we assumed as effective depth equal to 200 mm. Okay, so the required value should be less than the provided value, but here is the required value greater than the provided value. So the section is redesigned. Okay, so this is the most important point. I have to remind it. Required depth is should be greater than, sorry, should be less than the provided value, but here it is inversely proportionate. Okay, therefore the section properties have to be redesigned. Okay, so again the depth so the depth of the beam is increased as 250 mm. Okay, so in first step or first trial, uh, we took effective depth as 200 mm, but here in trial 2 we take as effective depth equal to 250 mm. Therefore overall depth equal to uh, add the effective cover, which is nothing but 50 mm, therefore 300 mm. Then next step is same step, effective find the uh, effective span and load calculation, then moment calculation. Okay, so these steps are uh, calculated based on trial 1. Okay, the next step is mu limit. So limiting moment of resistance, say qbd square. So 16.875 kilonewton meter. Okay, so uh, uh, if we are going to design as singly reinforced beam, the condition is m should be less than mu limit. Okay, so suppose if m greater than mu limit, then we will go for doubly reinforced beam, that is over reinforced section. Okay, here therefore we check uh, or we compare m and mu limit values here. Okay, so here m value is 16.369 kilonewton meter. Mu limit equal to 16.875 meter. Okay, so therefore m less than mu limit. Mu limit means maximum, ultimate, extreme. So mu lim here greater, therefore design as under reinforced section. Under reinforced section means the tensile reinforcement is fail first. Okay, so next is reinforcement calculation. So main reinforcement. Okay, so or a longitudinal reinforcement. So to find the, in order to find the main reinforcement, the formula is to be used as m divided by sigma st into j into d. Okay, apply those values and get the ASTF, required AST, that is 316.309 mm square. Okay, so in according to beam, we provide the detailing as in terms of number and dia of bar. Okay, as per SP16, the corresponding provided AST is two numbers of 16 mm dia bars. That is AST equal provided AST equal to 402 mm square, which is greater than the required AST 316.309 mm square. Okay. Then check for shear. So we have to check shear and deflection for flexural member like beam. Okay. Shear means uh, shear force. So the beam is failed based on the vertical forces like shear force. So in order to overcome this failure, we can provide shear reinforcement or bent up bars or inclined bars in support. Okay, so this is the most important failure occurs in beam. Okay, so how to rectify it? uh, so first step is nominal shear stress, that is tau v equal to v by bd. V is shear force, so already we found it, and b is breadth of beam, d equal to effective depth, so in trial 2. Okay, so then uh, tau c. So the concept is compare tau v and tau c value. Tau c is permissible shear stress, tau v is nominal shear stress. So permissible shear stress should be greater than the tau v. So if it satisfies, then okay, the beam is okay. Therefore, to find the tau v first, that is 0.205 Newton per mm square. So in order to find tau c, we need PT, that is percentage of reinforcement. The formula is to find PT, which is equal to 100 AST by BD. So AST means provided AST of main reinforcement, and apply these values, and we will get PT equal to 0.42 percentage. Therefore, according to IS 456, according to PT and grade of concrete, uh, we can take, or we can read out tau c value from IS 456, that is 0.2744 Newton per mm square. Okay, here tau v less than tau c, therefore hence safe. Okay, and save. So if tau v should be tau c, we can provide the shear reinforcement spacing as ASV into sigma st by 0.4 b, that is minimum shear reinforcement according to IS 456. ASV is uh, uh, area of vertical shear reinforcement. Okay, here two-legged 8-ohm dia bar we can use as stirrup or shear reinforcement. Therefore 2 into pi d square by 4 into sigma st value, here fe 415 steel. Therefore say the permissible stresses of steel is 230 Newton per mm square divided by 0.4 b. Therefore 192.684 mm spacing, two leg stirrups. So we can choose 190 mm. So spacing should be uh, uh, or spacing can be reduced than the already found value, that is 192.684 mm. Okay, then spacing. Okay, then deflection. So according to IS 456, the deflection condition is L by D actual less than L by D max. Okay, say L by D actual equal to effective span by effective depth. Say 17, L by D max equal to basic value into KT KC KF. Basic value is 20. KT is KC KF value 1. We can find KT value alone from IS 456 using the curve. Already we have seen in one way slab about it. The FS value is 0.58 F5 area of required AST by provided AST. Apply those values. We can get FS value as 189.39 Newton per mm square. Therefore, read out the curve. We will get KT equal to 1.62. Okay. Then L by apply L by D max equation, then we will get L by D max equal to 32.4. Therefore, compare L by D actual and L by D max value. Here L by D actual, which is less than L by D max. So hence save. Okay. So our design is okay. Our providing reinforcement like main reinforcement diameter, number of bar, then dimension of the beam, and shear reinforcement diameter and shear reinforcement spacing, all the values are correct. We conclude that all the values are correct. The last step is the detailing, most important. So you have to mention, or you have to mark in various color. Okay, here red color is main reinforcement. uh, uh, the tensile reinforcement is bottom reinforcement. The top reinforcement is here hanger bar. Okay, then when the vertical reinforcement indicates that vertical stirrups, and the cross section of beam is given in side. Okay, so this is the singly reinforced beam design. So if you have any doubts, you can ask me, and please work on in another problem. Thank you very much.